So we're back to weather again. Meteorology, again, an important aspect of geography, location, and distribution of weather systems is extremely important to our understanding of the Earth. Understanding the dynamics of the atmosphere is important to our understanding of the Earth. And the weather is often a volatile mix of temperature, air pressure, and humidity. All these things constantly changing for which creates changes in weather. But that's part of having an atmosphere. The air is fluid. Its temperatures are changing, pressure is changing, it's moving around. So that causes changes in weather. Go to the moon, no atmosphere, no weather. Now, the thing you have to understand about the atmosphere is there are several different distinct layers of it with distinct features. All these go to factor into making our weather. Another thing is there's the idea of the lapse rate. Lapse rate is the rate of temperature change with altitude. Generally, the higher up you go, the cooler it is. It averages about 3.5 degrees per 1,000 feet up to the tropopause. Jets flying at 30,000 feet, typically you see that Dallas Atlanta flight always going over us. The air sometimes is up to 100 degrees colder than it is at sea level. So yeah, it's pretty chilly up there. Why you see these old films of these World War II bomber pilots while they're always wearing coats because if they weren't flying the stratosphere, they're flying at 20,000 feet. It's generally a lot colder up there than would be on the surface. And up to the tropopause, it is the edge of the troposphere. Understand temperature scales. In the United States, we use the Fahrenheit temperature scale, the old conventional system. The rest of the world tends to use the Celsius metric system. And here's how you know the difference. Fahrenheit to get the Fahrenheit temperature, you go 9/5 times temperature Celsius plus 32. On this scale, freezing is at 32 degrees. Boiling point of water, 212 degrees. Fortunately, it never gets that hot on the surface. Celsius, again, based on the metric system. But Celsius, it's just the opposite. 5/9 the Fahrenheit temperature, subtract 32. This nice and even system where the freezing point is at 0 degrees and the boiling point is at 100 degrees Celsius. Made up that way because those were fairly conventional ways of understanding extreme temperature, freezing versus boiling point of water. Now again, air pressure can affect these points too. This is generally at sea level. So on the Fahrenheit scale, day in the 30s is considered very cold, but On the Celsius scale, a day in the 30s is a fairly nice spring day. 98.6 is normal temperature on the Fahrenheit scale for people. That translates to 37 degrees on the Celsius scale. And there's even another one, the Kelvin scale. This is mostly used by scientists, physicists, and astronomers. It's based on the idea of absolute zero. That is, that's the temperature where all motion in molecules stops. The atom itself freezes. The coldest possible temperature. And it goes up from there based on Celsius measurements. So 0 kelvins, and it's not 0 degrees Celsius, 0 kelvins, it's equal to 459 degrees below zero on the Fahrenheit scale. But 273 kelvins, that's equal to 0 degrees Celsius. Equal to 32 on the Fahrenheit scale. Similarly, 373 equals 100 degrees Celsius, which equals 212 degrees Fahrenheit. Astronomers especially use this, especially in talking about the temperature of stars and the planets and so forth. The surface of the sun is generally described as 5,000 degrees, 5,000 kelvins. Toasty. But again, all of it is also based on the idea of the measurement of motion of atoms. The sun's corona is considered to be about 2 million kelvins because all these excited ionized particles are moving very rapidly. But it's not used with, Kelvin is not used with Earth weather. Usually Celsius or, especially in the United States, Fahrenheit. Now the idea of temperature inversion. Remember, the lapse rate is not always constant. There are different factors affecting it. If air is warmer or often on the ground, that's called a temperature inversion. And you see that sometimes with some winter weather patterns. Might have a warm front coming through. And still have very cold temperatures on the ground. Especially as this warm front moves along. Got to remember basic physics. Warm air is lighter, so it rises. Cold air is heavier, so it sinks. And warm air can also trap warmer air on the ground, sometimes trapping pollutants. Smog is an example of this. And of course, the idea of air pressure. Air pressure, a lot of different ways it's measured. Measured in pascals, pounds per square inch, millimeters of mercury, so forth. But air pressure at sea level, generally 14.7 pounds per square inch. Higher altitudes, there's generally less air pressure. So, several you noticed, looking at the directions of certain food products you might buy, they have directions for preparation at higher altitudes because the air pressure is different, affecting cooking times and cooking techniques. And also, something very common in mountain altitudes is altitude sickness. Sometimes the air is so thin up in the mountains that people do get sick because of lack of oxygen. It's very common up there. But commonly, air pressure is measured with a barometer. Simple device for measuring air pressure. It's usually uses millimeters of mercury as its metric. That is against a thermometer, which is used to measure temperature. But mercury was the old way they used to measure temperature and pressure. Because the thing about mercury is it's a liquid, it's a metal, but it's liquid at room temperature. On down to 40 degrees below zero, that's when mercury freezes. So those old thermometers, they didn't go below 40 below zero because it just didn't work. One thing, usually doesn't get that cold, but also mercury freezes. When I was a kid, they still used mercury thermometers to check kids' temperatures. Basically, it was a little glass tube filled with mercury, and you put it in your mouth. Yeah, the problems are obvious, but that's what they had. But because it's a liquid, mercury, it expands and contracts with temperature and with air pressure. So, using these temperature changes, you can using these properties, you can measure temperature. Also measure air pressure. Um, so with the barometer, generally lower pressure equals stormy weather. Mid-range is fair, sometimes indicating change. Mid-range is kind of a transition point. High pressure, generally, again, fair weather. But you have 900 millimeters of mercury measured here. That is a stormy day. 950 to 1,000 indicates changing conditions. Usually it's good weather, but not always. Clouding up or clearing off, one or the other. 1,000 millimeters of mercury, just for example, that's generally a fair day. Also, it works on the pounds per, works on the system of inches of mercury too. For example, 28 to 29 inches of mercury, that's generally stormy. 30 inches of mercury, indicating change. Generally fair, still generally stable. 31 inches of mercury, fair weather. And that's how it generally works. Weather forecasters will look to changes in air pressure to see the approach of storm systems and indicating change. Very commonly used before there were such things as radars or satellites. In the old days, in the 50s and 60s, weather forecasters, they would have to go with barometers and thermometers and wind directions to forecast what the weather was going to be. They get it fairly close within a few days, but beyond that, it was really hard to kind of figure it out. But barometer temperature, changes in wind speed and wind direction, those are good indicators for changes in weather. Okay. Now, layers of the atmosphere. Generally, there are several layers of the atmosphere. We'll start off here at the ground. Lowest layer is the troposphere. Generally extends up to 7 miles, more or less. And at the top of the troposphere is something called the tropopause. Interesting enough, as these different layers of the atmosphere, there actually are very strong air currents at work, called the jet stream. Jet stream travels west to east, very high speeds, and it's broken into different layers. Arctic, subarctic, tropical jet stream. I call it that because if pilots can kind of get into the jet stream or close to it, that can help pilots going from west to east fly much faster. Basically, get that little tailwind behind them. But contrarily, if you're flying head first into a jet stream, it kind of slows you down. So can try to avoid it flying back west. But changes in the jet stream, its speed, direction, and even location, that can really affect the weather. For example, the jet stream drops really far south. That generally means there's an Arctic system coming in. There's cold air following in behind it. But because you're so close to the ground and all the sun's energy, you got a lot of that turbulence. So the troposphere, this is where most of the weather in the atmosphere happens because it's so close to the surface, because air pressure is at its thickest, closest to the major sources of water, oceans and the seas and the rivers, and because that solar radiation is warming the Earth's crust, that's creating changes in temperature. So if you're flying under the jet stream in the troposphere, it's kind of bouncy. So modern jets tend to fly in the next layer, the stratosphere. Most jets flying at 35 to 37,000 feet, they're flying in the stratosphere, above the clouds, above the weather. So there isn't very much weather in the stratosphere, so flying's generally very smooth. With pressurized modern jets, yeah, you can fly very smoothly at 35, 37,000 feet. No turbulence, no bouncing around. This layer is generally between 7 and 31 miles. There's something very interesting happens with the stratosphere is where the temperature is dropping in the troposphere as you get further away from the surface, higher altitudes, it starts rising as you go higher in the stratosphere. Yeah, it seems kind of counterintuitive, but that's what happens. Temperature generally starts increasing. Why? Because the air is thinner. Now you're measuring not as much air, so it's bouncing. The atoms are bouncing around a lot more. At the edge of the stratosphere, you have what they call the stratopolis. That's generally at 31 to 34 miles. But again, go out into the mesosphere. Beyond that, the lapse rate again flips over again. Temperature starts decreasing as you go further higher up into the mesosphere. Thirty-four to 50 miles above altitude. You're going to start dropping again. At the edge of the mesosphere, you have what's called the mesopause. Which is about 50 to 53 miles. Again, the atmosphere up here is very thin, so it can have some kind of weird things happening. It's the ozone layer that's generally about 40 to 50 miles up the upper level of the mesosphere. Now, above 50 miles, that's considered to be outer space. Still within the atmosphere, still very low Earth orbit, but that's basically considered outer space. The 1960s had a lot of test aircraft that would fly up past the mesosphere, past the 50-mile mark, and those pilots are considered astronauts, U.S. Air Force astronauts. But it's still a little bit of the atmosphere. You still got just a tiny little bit of atmosphere left. It's now considered outer space. But above that, you're entering a portion of the atmosphere called the thermosphere. Generally beyond 53 miles. Again, temperature keeps increasing with increasing altitude in the thermosphere. Now there are a couple of other layers of the atmosphere here that kind of go along here. One is the ionosphere. That is mixes with the mesosphere and the thermosphere, but it is generally of 34 miles. What happens in these upper layers of the atmosphere is, like I said, very little weather happening. Sometimes you do have small clouds forming up here in the mesosphere, in the upper stratosphere, but what are those made out of? Meteor dust. Actually, that actually happens. Small meteors breaking up in the upper atmosphere and dispersing. You also have in the upper ionosphere, the upper thermosphere, the aurora borealis. Because the sun is emitting all sorts of energy. That energy hits the Earth's surface, and a lot of radiation coming in at the upper levels of the atmosphere. The upper atmosphere screens out. Because of that, that's why this is called the ionosphere. Because a lot of the air up here is ionized. So what happens because you have all these ionized atoms up in the upper atmosphere? Well, it means astronauts re-entering the atmosphere, they have this blackout layer they have to contend with. Because it's so heavily ionized that radio communications kind of blacks out for a while while you're descending through the ionosphere. But also what happens is you're able to have radio signals, particularly like AM radio signals. They bounce off this ionization in the atmosphere, and this is your radio tower. The radio signals bounce off the ionosphere allowing signals to go far beyond the horizon. So we don't have to have necessarily line of sight communications. FM signals tend to work the same way, even TV signals to an extent. But there are only certain frequencies that work with this. But that's why on a clear night, sometimes you're out driving, some outlying radio signals will be more powerful than others. Like I say, sometimes it's a clear night, isn't much atmosphere, isn't much interference from clouds. The signals can reach up out of the ionosphere and bounce down and bounce way across the atmosphere. So stations like WWL out of New Orleans come in fairly clear on a clear night. Stations out of Dallas, even Nashville, come in pretty clear. And because of the ionosphere. And then beyond the thermosphere and the ionosphere is something called the exosphere. No weather up here. This is the top layer of the atmosphere. Basically, almost no air. And what atoms are, the molecules are there, basically, gravity isn't strong enough to keep it in place. They're just kind of drifting off into space. But don't worry, there's always a lot of activity here at the bottom, a lot of geologic activities. There's always, the atmosphere doesn't drift away. It's constantly replaced and constantly replenishing itself. So, those are the layers of the atmosphere. Now, you also have something called an isotherm, looking at weather maps. These are areas connecting areas of common temperature. For example, we'll say just for laughs, this is a map of the United States, and you'll see these temperature extremes here. These are isotherms. You can see it fairly commonly on weather maps. You also have what they call isobars, which connect areas of common air pressure. Isobars for air pressure versus isotherms for temperature. That's usually it's professional meteorologists using isobars mostly because most people look at the weather. All they really want to know is what's the temperature going to be? Is it going to be sunny or not? But to figure that out, especially over the long term, over the entire day, the meteorologists have to study all these factors too. Again, air pressure. Now, of course, you see these H's and L's on maps, high pressure versus low pressure systems. And sometimes they get very close together. That creates something called a pressure gradient. Remember, basic physics. Nature abhors a vacuum. So heavier air will try to fill in areas of lighter air. More pressure to less pressure. So these H's and L's get very close together. There tends to be a lot of wind between them. Because what's happening is these air masses are moving, and it's like a vacuum cleaner, it's moving towards areas of low pressure. Except basically trying to fill it in. Turns out that they kind of move around a lot. So, but yeah, there's all that very high winds. That's why there's often a lot of strong winds when you have storms coming in because air pressure is changing. Air pressure is moving out, it's moving around. Cold fronts and warm fronts, changes in air pressure. So a lot of wind moving around. And again, a lot of this does kind of depend on where you're at. We talked about smog a minute ago. Um, Mountains can produce a lot of effects. Mountains can kind of tend to block or slow down some storm systems. It's also you're in a flat plains area. That means temperatures and weather can change very quickly because there's nothing really to kind of block it. Um, you're near a large body of water. What happens there? Air is blowing, wind is blowing over a lake, tends to cool down the temperature. So winds near a lake tend to be a lot cooler. Also, have what they call lake effect snow. For example, go up here to New York, got the Lake Erie area. So New York, Pennsylvania. All this cold wind blowing down from Canada, what happens when it hits Lake Erie? The evaporating water is cooled, produces storms, and drops a lot of snow here on western New York. That's why last winter talked about they'd had that big football game canceled because they dumped 2 or 3 feet of snow was dumped on Buffalo, New York. That's common in Buffalo because so close to these Great Lakes, lake effect snow. Now suddenly go to Chicago. Chicago is on the west end of Lake Michigan, but the prevailing winds are blowing from west to east, which means Chicago is very cold up there right next to the lake. It doesn't get a lot of snow. Not compared to Buffalo. Why? Wrong end of the lake. Go up here to Michigan. Prevailing winds. Where's the lake effect snow going to be? Indiana and Michigan. Especially get into the Lake Superior area, a lot of very heavy storms, a lot of heavy snows in that area. But smog. California is known for having very strict emission standards on cars and in factories and everything else, very strict air pollution laws. But Los Angeles area still tends to have a lot of air pollution. Why? Geography. Explain how that works here. So here's the Pacific Ocean. Comes up here to the sea. You got the city. These huge, tall buildings, lots of freeways. Life is good. But then you got the mountains behind it. Hollywood Hills and everything. So here's what's happening. All this smoke from factories and cars is rising, but the wind off the ocean is blocking it in. Can't escape. It's this upper layer here, and just stops. And so, as more smoke and smog comes, a combination of smoke and fog. What happens is these pollutants are just sitting here, collecting up, because Los Angeles really is kind of sitting in a bowl. Surrounded by the mountains, but the ocean, you have all this wind kind of blowing it back all this the smoke and pollution back inland, where it's being blocked in by the mountains. So Los Angeles is kind of sitting in the middle of it. That's why their air pollution levels tend to be higher, because there's nothing really to break it up. That's why they have to have higher air emission standards, because otherwise the air wouldn't be breathable in some days. There's some pictures of people from the 1950s on heavy smog days in Los Angeles wearing gas masks. New York in the 1970s, they had smog alert days where people were told not to go outside because the smog was covering the city and couldn't get out, and basically it's hard for people to breathe. Sometimes you really couldn't even see very far at all because of all the smoke that kind of gathered in the city. But this is the example here of Los Angeles. The mountains are blocking it in. Now, one other big factor in the weather, of course, is convection. Like I said, warm air rises, cool air descends. But it's not going up and down in a straight line. It's a fluid, so it's swirling as it rises and descends. The direction of that swirl is called the Coriolis effect. tendency of the air to swirl in a particular direction as it air or any kind of fluid as it rises or descends. So low pressure systems, what you have is its air is rising, causing air pressure to drop. So the northern hemisphere, that means it's turning counterclockwise. Say England, anti-clockwise. Opposite for the high pressure. That air is descending. It's also curling downward, clockwise. And the southern hemisphere is the exact opposite. Low pressures spinning clockwise and counterclockwise for high pressure systems. But again, only the southern hemisphere. The northern hemisphere, counterclockwise, low pressure, clockwise for high pressure. So that's when you see hurricanes forecast on TV. Why in the northern hemisphere, these Atlantic and Pacific storms, they're always spinning counterclockwise. Again, because of the Coriolis effect. All that warm, moist air rising, causing low air pressure. So it's spinning counterclockwise. But in the southern hemisphere, their hurricanes turn clockwise. Same effect when you flush the toilet or drain the water in your sink or your bathtub. The water is swirling counterclockwise. But you flush your toilet in Australia, it does the opposite, clockwise. All because of the Coriolis effect. Another way you can see high and low pressure systems. L versus H. What happens with high pressure systems? Look at it from above. High pressure air tending toward the low pressure, but air spinning this way as it rises. Low pressure doing just the opposite. Descending and spreading out. It's not just pressure systems also, but it's also temperature systems. Warm versus cool. It's also a convection system. L is going this way, H is going this way. So you're close to the edge of land and sea, close to a large body of water. The difference in the heating of land and water is very great. Warmer air over land rises vertically, but it responds to the cooler air at the sea. So, go back to your example of Los Angeles. The wind is generally coming inland, but at night it's just the opposite. It goes out. Similar phenomenon with the mountain and valley weather systems. And in cities, you have something interesting, something called the heat island effect. Yeah, because different objects heat and cool at different rates. Concrete, it heats up very rapidly. So what happens in the city during the summer, it gets very hot. And that concrete makes it even hotter. So generally, the city is actually warmer than the surrounding countryside because grasslands they don't warm up as fast as concrete. Similarly, that means it cools off slower at night. Cities stay warmer longer, but out the countryside it tends to get fairly cool. So if you're living in a city out in the desert, very hot during the day, still warm at night. But out in the countryside, the sand outside of the city, it gets cold fast. Temperature drops way down. The heat island effect. So yes, this actually is a factor in the weather too. Difference between cityscapes versus rural areas. Now, every so often you may hear about something called the rainy season, called a monsoon. Generally, this is a wind that changes direction periodically, particularly in areas like South Asia. And the change in this wind direction basically brings a lot of precipitation and a lot of heavy rainfall. So in areas like Burma or Thailand, to get to the monsoon seasons, when the winds coming off the Himalayas, it rains for weeks on end. All it does is rain very heavily. And that affects agriculture and how people live. So farmers in these areas are completely dependent on the monsoon to judge the time of when to plant, when to harvest. And disruptions in the monsoon season that can be disastrous for them. So we get to precipitation. I've been touching on this a little bit. All coming down from convection and the Coriolis effect. Precipitation, that is any form of water that reaches the surface from the atmosphere. It can be rain, sleet, frozen rain, snow, hail. That is precipitation. What's the difference between them? Sleet is just pellets of ice. Basically, the rain is frozen in the upper atmosphere as it descends. Basically, it's just little drops of ice falling from the sky. Usually, because you have warmer temperatures aloft, starts as rain, then as it falls down and cools as drops of rain. Suddenly, freezing rain. This is rain that freezes on contact. Again, it falls as liquid rain because it's warmer up above, but because all these different air inversions and everything because of these front systems, but because the ground is basically frozen, the ground is cold, particularly like metal and glass, it freezes on contact with that. So a couple months ago when we had all these snow days, that's what was happening. It didn't snow. We had sleet and freezing rain. So the big buildup of ice. Snow, it's just pretty little ice crystals falling. Snow, remember, it's frozen from the sky, from clouds down to the ground. It forms its ice crystals. An interesting thing about snow, if you've never noticed, is it's always quiet when it snows. Because rain and ice, as it hits the ground here, that tap, 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 as it hits the ground. Snow is just gliding down. It doesn't really make a noise when it hits the ground. But what kind of precipitation depends on temperature and, of course, humidity. Humidity. This is the amount of water vapor in the air. Cooler air tends to hold in less vapor than warm air. Basically, sometimes you can feel it when it's about to rain. It's just the air is just so thick with the water vapor. But yet, cooler air tends to hold less vapor than warmer air. That's why these big high pressure systems that dominate in winter bring that colder air from up north. Why, after that first initial night or day of snowfall, why all of a sudden it's just generally clear for kind of cold for a couple of days because that colder air is not holding as much water vapor in the air. At 100% humidity, that is the saturation point. That is as much as it can hold. So if humidity keeps rising as temperature drops, that's when you get fog. Basically, cloud formation on the ground. Again, basic physics, basic chemistry. The air is so cool it cannot hold this water vapor, so that water vapor has to do something. So it starts condensing out of the air in the form of fog. So gives you another term, relative humidity. It's a little bit different from humidity. Humidity, remember, that's just the general amount of water vapor in the air. Relative humidity is percent of water vapor present versus what can be held at that temperature. Because remember, that changes with temperature. And that has a big factor in the weather. The percent of water vapor versus what can be held at that, compared to what can be held at that temperature. Gives us this next one, dew point. Again, this is where air pressure and temperature coincide. Dew point is the temperature at which condensation occurs. You may notice on a spring day you have these big puffy cumulus clouds. It seems like there's they seem so puffy up on top, but they're always flat on bottom. Again, because at that flat bottom, that's where the temperature is lower to the dew point level. So that water vapor starts condensing. These tiny little vapor droplets. Clouds start forming. Temperature at which condensation occurs. Dew point. Then you got what they call convectional precipitation. In our area, that's most of the precipitation we get. These very heavy, big, heavy thunderstorms. Happens is you got your huge old cloud here, the thunderhead, rising up, forming little anvil parts because of the upper level winds. But you can see them forming off in the distance in summertime. These towering clouds, they actually go up into the stratosphere even. This point here, which is dew point. So the anvil here. Can generally be about 35,000 feet. Again, just topping off into the stratosphere. So yeah, sometimes these big storms, they can be a hazard even for pilots flying in the stratosphere. And eventually, because they generally have to start descending into this weather. We also get to a point here where these clouds actually rise above the freezing line up in the upper atmosphere. So here's what happens. You've got warm air, warm moist air rising. And so you have this area called the updraft arising. But it starts cooling off. Water starts condensing. And around here at the top, and starts spinning around a lot. You have this massive downdraft. Happens this downdraft that's where the rain starts coming down. So warm going up. And cool coming down. I often have a lot of heavy winds associated with it because these tall clouds, these powerful downdrafts, that downdraft isn't going to stop the cloud level. It's coming right down to the ground and spreads out as it reaches the surface. So you can feel the wind as these storms approach. That's part of the downdraft of it. Sometimes, yeah, you can smell that ozone smell that rain in it. But again, because you have this updraft and downdraft, these contrasts in forces, that means there's a lot of turbulence in these clouds. That's why they often turn into thunderstorms. Most lightning you see, that is cloud to cloud, happening within the cloud itself or spreading from one cloud to another. Just basically static electricity built up because of these different forces, all these atoms and molecules rubbing up against each other. Again, most of the cloud to cloud, most of it taking place within clouds, but a lot of reaching the surface. And what happens is a lot of times because these storm clouds are rising above the freezing level, what happens when these water droplets get above that level? They turn into ice. All these downdrafts, they come down as ice very quickly, which is what is hail. And because of all this turbulence within these clouds, sometimes these little water droplets, they're starting down this downdraft, but they get pulled back, blown back up again, back above the freezing line. So what happens is another layer of water is attached to this little tiny little ice, little bit of ice, making it bigger and bigger and bigger. So it's why if you ever cut a hailstone in half, it looks like an onion layer, because that's how many times, basically how often it's had to go up and above the freezing line before it finally coming back down because of the downdraft and gravity. So these larger hailstones, yeah, that's because of very intense, very turbulent storms. Most hail melts before it reaches the ground, but what you usually have, though, would be pea-sized hail, but sometimes you have dime-sized hail or golf ball-sized hail, tennis ball-sized hail. Baseball-sized hail, that is very rare. That is a very intense storm. But those kinds of hailstones are very rare because gravity. It's just too much weight for the winds to keep blowing it back up into the sky. But yes, falling pieces of ice from the sky, that can be dangerous. It's another reason why you need to be inside when it's rain and hail out there, because one of the dangers of lightning, two, hail hitting your head can cause problems. You see what it does to cars and to roofs. So there's that. The other form is orographic precipitation. This is most common near mountains. We're kind of a flat area, so here across the south, so most of what we get is convectional precipitation. But again, because of prevailing winds and the Coriolis effect, the strongest storms in our area usually start out in West Texas, western Oklahoma, and just move along the Red River, steadily moving east toward us. Can they come from other directions? Yes. But the summertime pattern is usually from east to west. But even with those cold fronts coming down, and a lot of times these storms are moving from the southwest up to the northeast. Now, orographic precipitation causes the rise from changing elevation up instead of an updraft. Got your little ocean or body of water here. What happens is, got a mountain here, and so as a result of that, you've got the steam rising and steadily moving inland with the wind, and starts moving up the mountain. But it reaches the dew point line, forms into clouds, and starts raining on the other side of the mountain. Goes up, comes down. The term they use here is the windward slope versus the leeward slope. This area here is called the rain shadow. Windward slope is generally wetter because it's being exposed to that moisture from the lake region, from the lake or ocean. The leeward slope is often dry. Again, you see that out in California, out on the west coast. These types of rains are very common. This is why Seattle and Portland are so synonymous with rain, because you've got that Pacific air coming in, wet. It starts rising as it moves along. The wind blows along the mountains, starts cooling to the dew point. Clouds form, then rain. But also, it's generally wetter on the ocean side versus the non-ocean side. Again, get east of the mountains in Oregon or California, very dry, very arid areas. And I think of Oregon as being arid, but parts of it are. At least much drier than, say, Western Oregon or Northwest California. So that's orographic precipitation versus convectional precipitation we're used to in our area. So the orographic, can you have severe weather? Not usually. The dynamics aren't there. It just gets very wet, but of course that wetness can cause landslide stuff if there's enough of it. So we'll continue on with more weather next time here in Chapter 4. If there are no questions, we'll talk more about weather systems next time.